how do I even start with silicon carbide? How do I make that leap of faith? But what you're saying is that actually these products have been designed with a purpose. They've been designed with background. They've been designed understanding what the market is. So actually, if you're thinking about how you're going to power your next generation EVs, you shouldn't feel like it's a leap of faith. You should actually feel like it's a very natural progression. Hello IPXers, we are here at PCIM. Now, at PCIM, we talk a lot about silicon carbide and GaN. Everybody talks about silicon carbide and GaN, a bit like when we talked about AI at CES. So I thought it'd be really good to do an introduction about what's going on in silicon carbide. So I'm going to introduce you here to my good friend Amr Darwish, who is a Senior Director of Product Marketing and Market Development for Silicon Carbide MOSFETs at Vishay. So Amr, tell us.
Yes.
Why are we talking so much about silicon carbide?
Well, honestly, the way we do everything has changed in the world of technology, the consumer market, transportation, something like the internet that has exploded over the last 10 to 14 years, even more so than it was, requires things like larger data centers, better thermal management, higher power densities, more efficiency, so on and so forth. So
everything's getting more complicated. Everything's getting more complicated.
It's not just the electric vehicle, which of course is a huge part of it. There's a lot of industrial applications, more things into solar energy storage, and how efficiently are we doing that in order to power our homes, provide energy back into the power grid. It really expands beyond just the basic understanding of the consumer.
Yeah. So what you described there is a sort of ongoing. Nothing in the world gets less complicated, particularly in the world of high technology. We get more complicated. We had more features, we had more power, we had AI, we take computing into applications that never did have computing, and all of that has got to have a power source, and all of that has got to be efficient.
Right.
So there is legacy design. There are things where people were doing things and that they understand how things work. So then new technologies come along, like silicon carbide, like GaN. Mm-hmm. So just give the IPX followers some idea of why, or the transition, the process by which you would consider silicon carbide in your application, and then what the benefits are if you do that.
Right. So, there's an old adage in power semiconductors, if you can do it in silicon, you do it in silicon. So obviously there's still a great market there. Where silicon carbide starts to get into play and becomes more interesting to design and system engineers is when you need to get into higher power densities. You need much better thermal conductivity, and you need higher performance than silicon can provide at that same voltage level and power level. So, for example, I'll use EVs, electric vehicles, as a great, the largest example.
Just let me ask you a question. One of these things that people use the things like power densities all the time.
Sure.
So, what's your definition of power density? What are the implications? Are you saying that it's the system and it needs to get more power out of it, or the system's getting smaller and therefore what you expect from it is in proportion to the size of that system? So, what's your definition of what that means?
So from a silicon carbide MOSFET perspective, for example, the devices that I'm involved in, that is that device being able to output and operate at a higher voltage, meaning the end system is operating at a higher power output.
Excellent.
So that's why I was going to use the example of an electric vehicle.
Yes.
It takes a lot of power to move such a heavy, large object.
Yeah.
And that's very difficult to do in traditional silicon at the same efficiency levels as silicon carbide, managing thermal, so heat dissipation, as silicon carbide. Where you start to have issues is the cost-benefit ratio. So that's why I said if you can do it in silicon, you do it in silicon. The economies of scale are already there. It's a very mature material and technology. Where we are starting to see the advantages of silicon carbide are there's some instances that silicon just can't do it, or at least not do it efficiently. And silicon carbide prices in terms of end product, the supply chain, meaning raw materials, manufacturing costs, are starting to come down.
Yeah. So that's quite an important message, isn't it? For if you're looking at a system now, let's say you take when we talk about EVs now, we're not talking about 5 years ago we might have been just talking about Teslas and high-end consumer, but EVs now are we're talking about EVs in all sorts of applications.
Right.
It's quite a throwaway comment in EV,
right.
but we're seeing it in industry, we're seeing it in agriculture, we're seeing it in transport.
Right.
So all of a sudden, this is everything that's going on.
And don't forget, everything has an ecosystem. So if you have an electric vehicle, where are you charging that?
Yes.
So you have things like an off-board charger, which is the charging unit that's outside of the car. You have an onboard charger, the charging unit inside of the car. Those also require high power input and very high frequency type applications, which silicon carbide is very apt for.
Okay, so we're talking about you've described how the advantages of silicon carbide, the point at which you or the advantages of silicon carbide. So you call it higher density.
Power density.
You've talked about the fact that the prices are coming down. So where you might have seen this as being some sort of distant technology to you, now it's a very feasible area.
Yes.
So if I'm working on a legacy design, or if I haven't been using silicon carbide before, what are the design entry points? What are the if we're honest, I might be afraid. I might be thinking, right, I'm going into an area that I don't understand. So what would be for you, as somebody who's absolutely understands this technology probably better than anybody else on the planet, what would be your advice to someone who's thinking, okay, I need these higher power densities. I know it's something that I can potentially afford. I know that it's a more efficient way of doing it, but there are design implications.
Sure.
So you just help us understand that what happens when you go from a legacy solution to this kind of solution.
Sure. Well, to clarify where you're coming from, you wouldn't change from let's say a super junction silicon-based product to a silicon carbide product on an existing design.
Right.
That's probably something that wouldn't happen.
Okay.
Where you would start to think about that is, for example, and this is very true in electric vehicles, even the ones that use higher voltage silicon versus silicon carbide, or maybe even use silicon carbide at the time, going from a 400 volt electric vehicle system, for example, to an 800 volt electric vehicle system, which is now the trend, you are going to have performance needs that silicon carbide is much more apt for.
Right.
And just does more efficiently.
Yeah.
And in terms of, again, cost implication, yes, the supply chain and the manufacturing of the silicon carbide is also coming down. On top of that, when you use something like silicon carbide with better thermal connectivity, you no longer need some of the other peripheral components around it that manage heat.
Oh.
So heat sinks, for example, that's removed. Smaller footprints, you're not paying for those heat sinks anymore. You save costs there. So you might look at a silicon carbide device and say, oh, that costs X, and this silicon solution costs Y. Well, it's also X minus the peripherals around what would have been around the silicon product.
Right.
And the fact that you have a smaller form factor as a result of not needing extra components.
Yeah. So okay, not a very good question for me. Apologies for the not very good question. But sort of trying to understand what you described there is not so much a design implication, it's actually understanding how you're going to make your system more effective, how you're going to be spending less on the peripherals that are around that system, and making so it's not just an efficiency thing and potentially a cost saving thing, but it's also making things smaller and more efficient and buying less components, so making the design more elegant, if you like.
Sure. And, I would say it's both. It's everything that you just said, plus the fact that a silicon carbide device at higher blocking voltage is going to perform better in both DC and AC parameters. So it is still a design perspective technically, but there are these other more tangible things that you benefit from using silicon
so
carbide.
One last question, because the whole point of this was it was an introduction into silicon carbide. We certainly, if I was going to be on the video, it couldn't be a PhD in silicon carbide. It had to be very much a beginner's guide. So if you are going to go into that adventure of deciding that I want those higher power densities, I want that more efficiency, I want to spend less money on the overall system, what's the starting point? How do they come to you and have a conversation with you? How do they evaluate it? What's the process by which they start that journey?
Sure. Well, the goal is always to have your products and technology capabilities known. by design engineers, system engineers. Then they really, design their systems, and then they understand, okay, these are the parameters I need to meet in order to make this system work, right? So based on that, then they'll understand, okay, I need silicon carbide. If you're making a main traction inverter for an electric vehicle, I know I need a 1200 volt silicon carbide MOSFET with very low RDS on, and so on and so forth. Now, I want lower RDS on. I don't necessarily want to throw the AC parameters out the window. I still care about that. So it's really a system level understanding.
Right.
And we, as a supplier, are also not just selling components in a shotgun approach. We listen to our customers and what they're building. This is what actually informs us of what products we actually develop and put on our roadmap and eventually design and manufacture.
Right.
Yeah.
So they do, you have to do that in partnership with them. So you have to sit them down and really understand the process. So their first step has got to be come and talk to you.
Right.
They're not going to be going clearly. They're not going to be going to their local distributor and ordering 10,000 off the shelf. That's not what's going to happen. They're going to have a deeper technical conversation about how they solve these problems and how they integrate.
There's absolutely the channel in place for distributors in silicon carbide MOSFETs, for sure. What I'm talking about, these larger system level discussions come with OEMs, tier ones, things of that nature. For example, we have Vishay who are rolling out our first generation of silicon carbide MOSFETs within this year. The reason that the way that we obtained which products we should roll out first, and making sure that we do that well and in a controlled way, was we really went out, talked to the customers, looked at the market and said, okay, which products are going to give us the greatest visibility and opportunity,
right,
and go from there.
Right.
Again,
so you've not using a pun, but you've not done it in isolation. You've absolutely engaged and understood the market in order to cover off all those things that we talked about at the start of the discussion.
It is.
Which should make that process much easier, because you've been designed to be ready.
It's very collaborative.
You've been designed for purpose, deliberately.
It's very collaborative.
Right.
And when you start to have those conversations, and you have your product portfolio, future development roadmap, so on and so forth, then you already know what the market wants.
Yeah.
They've told you.
Yeah.
And that's where something like distribution comes into play. So now, maybe smaller manufacturers of XYZ devices and products go to distribution houses and say, I need XYZ, and it's there. It's already there. And, they can maybe buy them in smaller quantities and so on and so forth.
From everything that you've described here, we talk about, as I started at the start, talking about AI, and for a lot of people it'd be, where do I even start with that? And the whole point of this discussion was to say, how do I even start with silicon carbide? How do I make that leap of faith? But what you're saying is that actually these products have been designed with a purpose. They've been designed with background. They've been designed understanding what the market is. So actually, if you're thinking about how you're going to power your next generation EVs, you shouldn't feel like it's a leap of faith. You should actually feel like it's a very natural progression.
It was not created in a vacuum.
Yeah.
Silicon carbide, in terms of a technology and a concept, has been around for a long time. The market didn't dictate that it was absolutely needed. Again, now you have these applications, electric vehicles, solar energy, so on and so forth, that require this kind of performance and quality and reliability, so on and so forth. So the market dictated when it was time for silicon carbide to come in. Right.
Very good. Okay, well, I think that concludes our chat with Amr from Vishay. What I set out to do on this talk with Amr was to sort of give you the security to feel that you can go and explore silicon carbide. You should feel very comfortable if you're looking at a solar application or an EV application. It's ready for purpose, it's fit for purpose. Come and talk to Amr and his team and see how you get the advantage of these power densities and these more efficient systems because they're fit for purpose and ready to go to market. Thank you.
Yeah, thank you. Appreciate it.
Hey, yo, where my engineers at?